dynamic measurements. He is a fellow of IEEE. So let's welcome Dr. Mani Subramanian for today's seminar. Back to you, Mani.
Thank you, Anamika. Something you didn't mention. I'm the substitute speaker today.
Yes, sorry, my apologies. So yeah, Dr. Subramanian has been very kind to actually take over the slot for today. So thank you so much for that.
Yeah, our previous schedule changed because PSEP moved the seminar to next week, and we didn't want to leave this open, so I volunteered to give the seminar today. Thank you very much for the long introduction, Mika. And today the presentation is about, let me see if I can find it. Just an overview of oscillations in power systems. Can you see the screen, Anamika?
Yes, we can. Yep. Up, can you hear me? Yes, we can see the screen. Okay, great.
Yeah, thank you. So when we say oscillations, this is a concept that is associated with small signal stability. We have different concepts in the power grid: voltage stability, small signal stability, transient stability, frequency stability, and our discussions today will be focused on the concept of small signal stability. And this has to do with oscillations in the power grid. And we have oscillations all the time from load fluctuations, from changes in the power grid, but most of these oscillations will be well damped. And this is in fact a requirement for small signal stability, that any small perturbation or fluctuation should come back to normal steady state. And that's what we would like to see for a secure operating condition. But what can happen is sometimes because of either some really dramatic changes in the operating conditions, or because some control systems were poorly designed, or some control systems fail, we can end up with oscillations. And we will see several examples in the presentation today. And so when something like that happens, we say it is small signal instability. And this can lead to one of two consequences. Either it can lead to sustained oscillations or growing oscillations, and both of them are problematic for the power grid. So mathematically, we can show that we end up with small signal instability when some of the eigenvalues for the linearized system at the equilibrium point become negatively damped, or for those of you who have background in system theory, when the Jacobian has eigenvalues in the open right half plane. And we will discuss this concept both using model-based analysis and measurement-based analysis, and what can be done for detecting and mitigating oscillations in the power grid. So first, basic review from physics. We know that a normal pendulum is at a stable equilibrium point. And we say this because if there is a small perturbation, say the pendulum moves to position 1 on the left side, when we have normal friction, which is positive damping, the pendulum will swing back down towards the bottom, and then because of the momentum, it will go a little bit far on the other side. But because of friction or damping, it will swing back and forth, and after a few swings, it will settle back at the equilibrium condition at the normal position. So this is what we mean by a small signal stable system condition. Whereas what can happen, suppose for some reason the damping becomes negative, or we can imagine a negative friction. So in this case, as the pendulum swings down in the right side of the picture, because the friction is negative, the position of the pendulum will go farther than where it started from. And this will happen as it swings back and forth. And as you can imagine, after a few swings, the pendulum will go into full circles and possibly will lead to some kind of a breakdown of the pendulum. And this is exactly what we want to avoid, because if something like that happens in the power grid, this can lead to generators losing synchronism, or in the worst case, generators and equipment facing some damage. And these are expensive devices, so we have to avoid such consequences at any cost. So a basic definition here, and this is from our Western system working group. By oscillations, in the power grid, we in fact have some kind of oscillations or energy exchange happening all the time. And this is the normal power transfer that's occurring at 60 Hertz. We know that the power or energy is flowing back and forth from the generators to loads. And this happens as an alternating waveform at 60 Hertz. But the problem is when we have such energy exchange at frequencies other than 60 Hertz, so we call this as asynchronous periodic exchange, then this leads to problems, because this can lead to vibrations and rotor fatigue, and it can seem as power fluctuations. In some cases, customers have had light flickering depending on the frequency. This may be at low frequency, high frequency. So the presence of such poorly damped or undamped oscillations is problematic for the power system. We say that the oscillations should be well damped all the time, and that's how a good system should be operating. We can have another phenomenon, and this is called as forced oscillations, where we can have oscillations being injected into the power grid by an external mechanism. And this could be because hydro generator is operating in rough zone, and it causes oscillations on the hydraulic side, which shows up as fluctuations in the power output. Or it can be because some control is going back and forth between minimum and maximum, and that can again lead to fluctuations in the voltage magnitude or in the exciter component or in the governor valve position, and all of those are examples of forced oscillations. Again, our responsibility as a power system operator would be to locate and identify any such cause of oscillations and make sure that the system returns to well-damped normal operating condition. And here is an example what we mean by a well-damped oscillation, and this is an animation that was done over Power World tool and this is done using simulation. So we took the Western grid model and then did a transient stability or a dynamic simulation using positive sequence model, and then we animated it using Power World. So here is a disturbance, and you can see that the energy starts swinging up and down from north to south. But the good news is within 10 seconds, the frequency has returned to 60 Hertz, and that energy exchange has settled down to steady state. So this is the ideal response, where within 10 seconds or within a couple of swings back and forth, the oscillations have damped out. So we say this is a good response from a power system. And if we took a measurement, and this is actually a time plot from a recent brake test in the Western power grid, we can see again, just like in the animation, there was a disturbance, but the transient or the trajectory settled back to equilibrium within about 10 seconds, or in this case, in about 3 swings. So this is a well-damped response, and this is a good behavior from the system. Conversely, let's look at a case when we say the system is poorly damped. So here again, it's the same disturbance, but the system conditions are different. And now you can see that we are at 6-7 seconds, and still the energy is swinging back and forth from the north to south and south to north. So for a few seconds, the north has higher frequency, and then after a few seconds, it's the south which has higher frequency, and vice versa. So this is what we mean by a periodic oscillation. And in this case, the oscillation is at about 0.2 Hertz, or each oscillation period is about 5 seconds. And now we are at 40 seconds and still the oscillations are going on. So in this case, in fact, it would have continued for several minutes because the oscillations are really poorly damped. And even at 50 seconds, still the frequency has not returned to 60 Hertz and the oscillations are continuing. So this type of phenomenon or this type of response we want to avoid, because when we have sustained oscillations like this all over the system, that can cause potential damage, or it can lead to some inadvertent relay action. Some generators can get tripped, and that can lead to other consequences. And the worst case will be when the transient itself is unstable, and that can lead to breakup into islands. So here is an example again from the real system back in 2000, when Alberta separated from the rest of the Western grid. You can see the oscillations lasted a while. It took about 60-70 seconds for the oscillations to return to a nominal equilibrium or steady state condition. And here we could show that the damping was around 2% in terms of the damping ratio, and that would be unusually low for where we want to operate the system. So this is an example of a poorly damped response. Next, we will see what we mean by a local oscillation versus an interarea oscillation. So local oscillation is a phenomenon where the oscillation mostly affects one small part of the system, mostly maybe one generating plant. And in this case, we introduced some control issues in one of the major power plants in our Northwest. And so you can see mostly it is one generator that is causing or showing the oscillation, and it is maybe swinging with respect to a couple of other generators which are nearby. So this is an instance of a local oscillation, and the key difference is the bulk of the grid is not seeing the oscillation, or the oscillation is not being experienced by the generators which are far away from where the oscillation is occurring. So this problem, when we have a local oscillation, is more tolerable compared to when we have an interarea oscillation. And here is an example of a local oscillation, and this was a faulty valve at a power plant in Montana, caused governor to be flapping back and forth between some minimum and max value, and that resulted in a 1 Hertz oscillation. So the oscillation period is about 1 second between or for each swing. And this lasted for several minutes until this was corrected by the power plant. So again, the key difference, as I want to emphasize, is if you imagine, if you remember that animation versus what we see here, an interarea oscillation involves a vast portion of the power grid, and this would be problematic and in fact more difficult to control and mitigate because it involves so many generators swinging against other generators. So interarea oscillations are more problematic compared to local oscillations, which can be handled by possibly the generator getting tripped from the grid, or by taking some control actions like changing the schedule at the power plant. So let us see how we can analyze these oscillations. There are fundamentally two different approaches. What we used to have till about 20 years ago was everything based on models and model-based analysis. So this includes modeling the interactions of the generators and controls across the power grid. We would write differential equations for the generators, governors, and exciters. And now with the large-scale introductions of wind and solar, the dynamics is getting even more complex because typically they involve discontinuous or more discrete type controls, which is becoming a challenge in our modern analysis. But the main concept is we can describe the dynamics by using some mathematical equations. And so we call this as the system stability model. And in power systems, being a network system, they fundamentally consist of two parts. One is the power flow equations, which describe the transmission network. And we have the individual dynamics of the components, such as generators and controls. Good news is for small signal stability analysis, for oscillation analysis, we can linearize the nonlinear model into a simplified linear system description. So we can calculate the equilibrium point, which is basically the power flow solution. And then using that, we can linearize and find the Jacobians and come up with the system matrix. Then we know from linear system theory that as long as all the eigenvalues of J have negative real parts, the system will be well behaved and it will be stable. So for small signal analysis, the eigenvalues play a crucial role. And in engineering, we call them as the modes of the system. When we say we have a mode with real part alpha and imaginary part beta, beta is significant because the imaginary part tells us what will be the frequency of the oscillation response that corresponds to that mode. And again, one of the nice properties of a linear system, any system disturbance or response can be decomposed into a linear combination of the fundamental modal responses. So these responses are important in determining the full system response. So the imaginary part gives us the frequency, and the real part will tell us how quickly the transient will damp out. So the damping, which defines whether it is well damped or poorly damped, is defined by the ratio between the real part and the diagonal or the magnitude of the eigenvalue. Roughly, we can calculate this by alpha divided by beta. Usually, we represent the damping ratio as a percentage. The question that we wanted to know, how quickly does the response damp out? Does it take 10 seconds or does it take 50 seconds or does it take minutes? That, as it turns out, will mainly depend on this mode damping ratio. The theory says as long as all the modes in the system have good damping ratio, which we say from experience that it should be above 5%, then the system will be well behaved and the response will be well damped, like we saw in the first animation. And again, for a complex power grid like the Western power system, there will be thousands of eigenvalues and thousands of oscillatory modes. What we are saying is every one of those modes should be well damped, and that is one of the requirements of a well-designed power grid. The good news is most of those modes will not even be seen because the damping is so good. Typically, maybe a handful of those modes will show up in our system response, and they are the important modes for system analysis. And we want to make sure that those modes are indeed well damped and they correspond to our design criteria for how we want to operate and monitor the power system. If any of the modes becomes poorly damped, they will start showing up in the responses. And if any of them become zero or negatively damped, we may be in trouble. Again, another concept from linear theory, and this is important for understanding the modes. And this will tell us how we can tell apart between the local oscillations versus interarea oscillations. That has to do with the eigenvector. So if we look at the right eigenvector associated with a mode, and if we see what are the dominant components of the eigenvector, that can point to whether it is a local mode, in which case the eigenvector mostly comes from the states of one generator, or if it involves states from many generators, like we saw in the interarea oscillation, then it is a more complex mode, and these are referred to as the interarea modes. Some of the common modes that you should be familiar with: 0.25 Hz mode is a north-south mode in the Western system, and another, again, equally important mode is a 0.4 or 0.37 Hz north-south mode. And the mode shape of the two modes are very different, and I will explain this a little more in another event that we will analyze later in the presentation. In the Eastern interconnection, similarly, we have many interarea modes which we pay attention to in terms of operating the system. And here is an example of what happens when the mode becomes negatively damped. So this happened in our Western system back in 1996. The system was experiencing unusually hot weather conditions. In fact, we are seeing a lot more of those these days. And there was a large power transfer from Northwest to California. With those operating conditions, we lost several 500 kV lines in the Northwest because of trees growing too tall and touching the transmission lines. And also there were some relay failures which led to tripping of generating plant. So the system ended up in a severely stressed condition. And as you can see, the system started showing slow, small oscillations. And as the system event progressed, we lost more generation because of, again, faulty relay action. And as the generator started tripping, the eigenvalue moved further and further into the right half plane. And as we know, if we have an eigenvalue or pole in the right half plane, that will lead to exponentially growing oscillations. And that is exactly what happened during this 96 event. The oscillations grew from about 10 megawatt at the beginning at the 10-second mark to about 2000 megawatt at the 75-second mark. So in about 1 minute, the oscillation had increased in amplitude by a factor 20. And the operators had no time to react. This happened in about a minute. And at that time, we didn't have any procedures for tackling or monitoring these oscillations. This was one of the first implementations of phasor measurement units. So we were able to just see the oscillations, but we didn't really have an experience on how to deal with such an oscillation. So when the oscillations became so large, several transmission lines tripped out because of, again, relay misinterpreting the oscillation, or in fact, the current again started becoming so large. And as the lines tripped, the northern generators lost synchronism with the southern generators, and the system broke up into many islands. And there was severe load shedding in California and several southern power companies. And so this was a major blackout, and this was caused because the system ended up in a small signal unstable condition, or the eigenvalue drifted into the right half plane. Later, we have made so many design changes in the Western grid that the mode has been well damped in recent events. And I showed an example where it was well damped from a recent break test. So how do we analyze these using measurements? Models, one of the problems and one of the challenges, in fact, I should mention this, in the 96 event, it turned out when we simulated the system using planning models that were used for determining the tie line limits, when we replayed the same event conditions as the system faced during the blackout, with all the trippings, the system remained stable. So the model showed the system to have been operating nominally, whereas the real system, we had a severe blackout. So that led to a lot of improvements in how we model the system. And in fact, West has invested a lot of time and effort in improving and studying models. Now we are facing new challenges because of renewables. Modeling and analysis of inverter-based resources is becoming a new challenge because many of these are proprietary devices and the models are not well known for power system planners and operating engineers. So slowly, the measurement-based approaches have become more popular. As system conditions change, the measurement-based analysis can point to sudden changes in the damping levels of modes or the emergence of oscillations. And this has become one of the main applications of phasor measurement units in the last 20 years. So when we talk about PMU analysis, we have two kinds of oscillation methods that are available in the literature today. One, we can think of the system response during normal operating conditions as the system is getting perturbed by small load fluctuations, which tend to be like a white noise. So we can think of the system response as a stochastic response from the white noise input at the load buses and at the renewable generation. And then the response can be analyzed using linear signal theory, and we call this as ambient modal analysis. Or conversely, we can wait for when there is some switching or some tripping in the system, and that would be like a step change in the system condition, and that will lead to exciting of the modes and a transient response, which can be analyzed again using linear system theory, and we call this as ringdown analysis or event modal analysis. So I will briefly describe the methods for each of those types, and then we will move on to an example. So the idea is we will collect the PMU data and then see if there is some event that can be detected by using some kind of anomaly detection tool. So as soon as we detect an event, we can do the event modal analysis. And we will be continuing with the ambient analysis in parallel. And usually we like to cross-check if the results from the two engines match, because it's after all coming from the same system. So the results should be close. When we see a low damping alarm from one engine, that should be consistent with what we see with the other engine as well. And when it passes various consistency checks, then we will issue an alarm or alert to operators. And this has been implemented. Our group has developed multiple algorithms over the past many years. And we have these algorithms built into the OpenPDC platform as optional or as built-in action adapters. Just a quick review of the algorithms for event engine. We have developed some new algorithms, and there are many that have been available in the literature. And then also for the ambient analysis, we have proposed some methods, and there are also others in the literature. Then we tested and selected a few of them which work well together, and we built this into a toolbox that has been since implemented at many companies. And also it has been built into many commercial tools. So in the case of modal or ambient analysis, we use time domain method and the frequency domain method. Again, to provide some complementary analysis, each has its own advantages and challenges. And for real-time tools, it's good to have redundancy. So we like to use at least 2 algorithms to cross-check the results with one another. Quick overview of the theory. Like I said, we consider the system for small signal analysis, which will be like a linear time invariant system. Then we can model the loads as white noise. We can look at the outputs, and we can show that the outputs will have characteristics of the system transfer function. And this is because if you think of the white noise in a frequency domain, that's basically like a constant power across all the frequencies. Whereas when it comes through the system, the energy in the signal will get emphasized at the mode frequencies, or when there is a strong mode that is observable in the data or in the measurements. And we can show that the peaks in the power spectrum density will correspond to the main modes of the system, and the shape of the signal or the shape of the power spectrum density in frequency domain will tell us about the damping. If it is flat, that means it is well damped. If it has a sharp peak, that indicates that it is poorly damped. And in fact, we can show the frequency domain component of the power spectrum density near a peak frequency is like the impulse response, and we can extract the mode frequency, damping, as well as mode shape from this analysis. And again, for that August 10th, 1996 event, we played back the data that was collected during the event into the new tool that we have developed. And this is now the other tool, which is the stochastic subspace identification, or the time domain tool. And you can see the system was well damped about 10 minutes before the oscillation started. Then there was a 500 kV line trip, and that reduced the damping from about 8% down to about 2%. And it was at low damping for about 5 minutes. Then the generation tripping started, and that pushed the damping from positively damped to becoming negatively damped, and that led to the exponential divergence. So the good news is we have tools available today that could have predicted the presence of poorly damped system conditions well before the system collapsed. So we had about 5 minutes when the system was operating under poorly damped conditions. So 5 minutes, possibly the operators could have taken some corrective action, such as changing some tie line flows, and that could have prevented the consequences. And the other analysis is called as Ringdown analysis. And here what we do is we look at the system response, and we know by theory this has to be a linear combination of exponentially decaying modal responses. So why not find that linear combination, and that would tell us what are the frequencies of the modes present in the response, their damping ratios, and the mode shapes in terms of which mode is present more in what signal. And this can be done by writing the transfer function as a set of residues, and then we can convert them to the discrete domain, and we can show that it becomes a simple, like a least square fit, to estimate the modes as well as the mode shape. There are various ways to do this linear combination, and some of the more popular methods are listed here. You are encouraged to read the literature. One of the challenges we see is the system modal estimates can change with time because of some switching that happens during the event or because of nonlinearities, and that can lead to a false alarm. So for a real-time tool, we have developed various cross checks by using multiple moving time windows, and then we check the estimates from each of those windows, or also we check whether it is consistent by looking at different algorithms. And this has proved to be effective in handling some of the data quality issues which may come up with the real data. Next, we will look at how we can use these tools to analyze a real oscillation event and a more recent one. The previous one was 1996, and this happened a few years ago. Again, in this case, this is an Eastern system oscillation, and this was captured by a network of PMUs that UTK has developed. These are all PMUs implemented on the customer side, on the distribution side. So the data is publicly available, or it is communicated from these locations to the server in Knoxville. And using the data, they have created this animation. So I'll just play from the middle of the event, and you can see the oscillations are seen throughout the Eastern interconnection. So this was a major event. Fortunately, it didn't lead to divergence, so it was not catastrophic, leading to a blackout. But this was a case of sustained oscillations. And this lasted about 40 minutes. At the time, the operators didn't know where it was coming from or what was causing the oscillation. And since they were not clear, nobody took any action, which turned out to be a good thing at the time. So it turns out the oscillations were caused by a generator in Mississippi, and they were doing some testing and tuning of the power plant. And one of those power plant tests led to the power output changing at about 0.3 Hertz. And the oscillation was about 200 megawatt at the power plant. And what is surprising is this 200 megawatt oscillation was seen throughout the Eastern interconnection. So this caused a lot of concern at the time. And I wanted to show the mode shape. So if you look at the oscillation itself, if I can stop here, you can see that one of the characteristics of this oscillation, during the oscillation, Florida is in phase with North Dakota, and these appear to be two ends of the oscillation, and the Northeast is out of phase with Florida. So we have an interesting oscillation that we have Florida, which is out of phase with the middle of the grid, and that is out of phase with North Dakota. Consequently, North Dakota is in phase with Florida. So this type of phase characteristic, how the oscillation is seen across different portions of the grid, we call this as the mode shape. So if you look at the time plot, when the frequency is at the lowest in Maine, it is at the highest in Florida. So we say these two are out of phase. And also Florida is out of phase with Texas. And you can ask a question, Texas is not an eastern interconnection. That is true, but there is a small portion of Texas which is in fact part of the eastern interconnection, and most of Texas is its own interconnection. It's a separate grid, and that part which is just happens to be in the eastern interconnection is one end of this mode that is seeing this oscillation. And again, what we saw in the animation, Maine we can see is more or less in phase with or is Maine is out of phase with Oklahoma, or the middle of the system. If we take the magnitudes of each variation on different signals and also place them according to the phase, then we get what looks like a phasor diagram. And this is exactly what we call as the oscillation shape. So what we saw, Florida and North Dakota, they are more or less in phase, and they are out of phase with the middle of the system like Texas and Mississippi, and also Maine and Oklahoma. And the oscillation itself was injected. It was a forced oscillation at Mississippi power plant. But because it was resonating with an interarea mode, the oscillation was seen throughout the eastern interconnection. To understand this, we can look at the system modes that were present at the time using the ambient tool. And the dominant modes were at 0.2 Hz, 0.3 Hz, and 0.5 Hz. And the forced oscillation was at about 0.3 Hz. So it mainly excited the mode at 0.3 Hz. So when the oscillation started at the power plant, you can see the oscillation energy at 0.28 Hz got amplified a great deal because of the resonance phenomenon. And we also saw harmonics of the 0.28 at 0.56 and also at 0.84 Hz. And this can also be shown by using the time domain analysis using the stochastic subspace method. And here we can see estimates from moving window analysis like we see in a root locus diagram. So each cluster corresponds to a mode. So the system itself was well damped. There was a 0.3 Hz eigenvalue, which had about 10% damping ratio. But the forced oscillation, which is like 0% oscillation, interacted with the system mode and resulted in the resonance phenomenon. And this can be verified by looking at the mode shape. So the mode itself, again, has that same characteristic that North Dakota is in phase with Florida and is out of phase with the middle of the system. And that's exactly what we saw during the event. So this verifies that the large wide area oscillations were caused by the resonance between the forced oscillation at Mississippi and the mode at 0.3 Hz. Now the challenge for the real system operation, when we are facing this oscillation, all the generators which participate in the interarea mode would be showing the oscillation with possibly large amplitudes. Then out of these thousands of generators, how do we know the source is in Mississippi? we have to find the source so that we can stop the oscillation from interfering with the grid. So this is one of the big research questions that many researchers are working on. We developed some theory for how to analyze the resonance between interarea modes and forced oscillations, and we showed that three conditions need to be in effect for large amplification effect. And one of them, the frequency should be close between the forced oscillation and the interarea mode. The mode should be poorly damped, and those are the two well-known conditions from physics. In the power grid, being a wide area system or a network system, the location of the forced oscillation is also important. If it happens where the mode is strongly controllable, such as near the distant ends, then there will be strong amplification. If it happens near the middle, then it doesn't lead to as much of a problem for the system. So we could analyze the Mississippi event using those three conditions. We showed that the oscillation was in fact close in terms of the frequency. Fortunately, the good news was the mode was well damped. If it had been poorly damped, we would have had disastrous consequences, but the mode was well damped. And the location was a sensitive one, which is why the oscillations were seen throughout the eastern interconnection. And I forgot to mention, this work was done. I was involved in the study as a NERC contractor, and I helped NERC with analyzing the event. NERC voluntarily collected, or NERC collected data from various system operators, the TSOs and ISOs in the eastern interconnection. The data providers provided the data voluntarily. Then we collected all the data together and then used some of the tools developed at WSU for analyzing the event. And in fact, we analyzed many events and we published 4 reports on the modes in the different interconnections and also analysis of disturbance like the one I'm discussing now. So summary is the 2016 event, the resonance effect was mild because the mode was well damped. But this was like an eye opener that if the mode had lower damping, then the oscillations could have been much more severe. And this again emphasizes the need to monitor the damping of modes continuously, because we never know when a forced oscillation might appear in the grid. So this is my last slide. We have lots of open questions that we are currently working on. Like I said, with IBRs and power electronics, we are seeing high frequency oscillations at 12 Hertz, 40 Hertz, 50 Hertz. And the bad news is oscillations at those frequencies, our human perception is more, or I should say those oscillations are more perceptible by human eye at higher frequencies. So the acceptable levels of oscillations become smaller. So there is a lot of effort going on in understanding what causes these subsynchronous oscillations in wind plants and solar plants, and how to control them and how to keep them at a reasonable level. Inherently, these power electronic devices have these high frequency switching internally in how they interface with the grid. So the oscillations cannot be eliminated, but our responsibility is to keep them reasonable so that it doesn't cause a problem for the system operation. And then again, on forced oscillations, how do we know that a problem we are seeing is caused by a natural response or a forced response? And then if it is forced, where is it coming from? And either case, how do I take some control actions to improve the damping or to make the forced oscillations go away? So we have lots of open questions. And in fact, some of the seminar speakers in the near future may also be talking about these. So I will stop here and look forward to any questions you may have. Thank you very much.
Thank you so much, Mani. This was a fascinating presentation. We have a lot of questions actually on chat, and I'll try to summarize it since we are close to 6 minutes on time. So the one common question here is that what modification or design recommendation will you recommend to increase the stability of the system? So for example, what was done after 96 event? What was built in the Western system?
Yeah, that was a major event, and in fact, it led to many modifications in the operation and planning of the Western power system. One thing we realized, the tie line limits were too high for acceptable transfer from north to south. So the whole process of how we determine the tie line limits was revamped after the 96 event. And again, we can do post-mortem studies or even offline studies in planning type analysis if we have good models. So a lot of emphasis on cleaning up the models, doing periodic testing. So that has been a major effort. And then in terms of real time, now we have these tools which are constantly monitoring the system, trying to predict when we approach problematic system conditions, and to develop operating procedures for if we end up in a poorly damped condition, can the operators maybe lower tie line flows or trip some generators to make the damping get better? And again, to design controls such as SVC modulation, HVDC modulation, to introduce damping or to improve the stability of modes, either as a planning study or as an operational tool. So there has been, I would say, contributions across the entire power system stability area to improve the system. And this has been a big effort in the Western system. On the East, we are still getting started. Maybe I'll stop there.
Right. Sure. So actually that leads to a second question. So you mentioned about the planning model and the model mismatch to be one of the major causes and actually not understanding that this could happen, right? So what are the main factors for those planning model mismatch for the system that we have out there that we have actually planned for versus what we are really looking into?
Yeah, again, the mismatches were at various levels in the parameters of the generators and in the behavior of governors and exciters. Some of the limiters were not modeled or properly captured. The big realization was it's not just sufficient to have a generator model in the system, but it needs to be validated and verified. And since the time, now NERC has introduced standards that explicitly stipulate this as a requirement for reliable system operation. Now, how we do this for renewables is still being debated because of the inherent complexities in modeling and analyzing renewables. So far, fortunately, the contribution has been small, relatively speaking, compared to the rest of the generators. So I think we are getting away with ignorance, but this is going to become even more important in the future. So we need to pay close attention. We need lots of research on how to represent the IBR devices reliably in power system models and how we can design the systems to handle the intermittency and fluctuations in those operations.
Right. So I think that brings to my maybe the final question for today's talk. How do you think we'll be able to do it given there are so much of IBR devices? are being integrated at sub-transmission and distribution level. There is just a large number of those devices. How do we get away with the modeling challenge when we look at, not just the bulk grid, but actually sub-transmission and distribution, which are going to be affecting the bulk grid operations?
Yeah,
What's your
excellent.
recommendation for that?
Excellent question, Anamika. I think the answer is really in research and maybe forward thinking. And we have to, in my opinion, move away from a purely model-based design approach and embrace more measurement-based or online designs of controls, adaptive designs, adaptive monitoring of where the system conditions are. Because trying to come up with accurate models for these thousands and maybe millions of devices is maybe nearly impossible. So we need a new paradigm for how we do the design, how we operate the system. And that's something that we all should look forward to. It's exciting that we have to rethink our entire system in terms of how we can control and operate this power grid.
Great. Thank you so much, Mari. This has been an excellent discussion and Q&A session as well. I hope it gave our student a lot of points to think about. And thank you so much for covering up for today and for talking to us in ESIC seminar. And with that, I will call it a day for the ESIC seminar. Everyone have a great day. Thank you.
Thank you very much. Yeah, bye.